Okay, so moving on from the topic of superposition and linearity, we saw how different sources can be used to make separate circuits, and then these new separate circuits, they can be used to solve a complete circuit using the superposition principle. So now let's move on to a new topic which is called practical sources. Until now, the sources we have discussed, they were ideal in nature. For example, the voltage source that we were studying, we just assume that if it's a 12-volt source, no matter what the current going through it is, it can be 100 amps, it can be 10 amps, it can be 0 amps, the voltage would stay the same. But this is not true in real life. For example, I can actually prove it, that for example, if you have a car, and this is a very bad drawing of a car, but it has headlights. Whenever in a cold morning and you turn on the car, the headlights, they are initially dim at first, and then when the car just warms up, it becomes brighter. So there is something that is stopping the voltage from being this constant value. So in actual reality, that actual thing is an internal resistance, which I'll just call Ri. Now, for example, if someone tells you that there's a practical source, and the value of that source is 12 volts if the current through it is 0 amps. So whenever the current increases, because there would be a voltage drop across this internal resistance, the voltage drops to 11 volts. So now if you need to find the internal resistance, you can just see the voltage drop, which is 1 volt. So the voltage drop across this Ri is 1 volt. So the internal resistance, that would be 1 divided by 100. So this would be Ri. So this is how you basically implement practical sources in a circuit. You just draw an ideal voltage source and then add internal resistance in series with it. Alright, so the same is the case with the current sources. There is no such thing as an ideal current source in real life. The current's value, as I said, in an ideal source, it would stay the same no matter whatever the voltage across it is. But that's not the case in real life. So there must be something that reduces the current if it is added to the current source. So as we saw how current is always divided in parallel circuits, so there is an internal resistance in parallel to it. So this is the internal resistance in terms of the current source. So this is how you model practical sources. I'll just repeat it again, that for a practical voltage source, you just draw the actual ideal voltage source here, and then add a resistance in parallel with it and call it the internal resistance. For the practical current source, you just draw the current source and add a resistor in parallel to it, so as to reduce the current, and then just the entire other circuit here and whatever it is, and the same goes for here. So these are what practical sources are. But what advantage do we get by modeling these two sources this way? We'll just see now. So now let's just assume that I have these two circuits, and this is the internal resistance for the voltage source, and this is the internal resistance for the current source. So let's see what the relation is between these two circuits. So if I just write an equation to find VL, for this circuit, for the first circuit, I can just say that, for example, if I just use the voltage division rule, VL would be Vs times RL divided by RL plus RS. This is the voltage division rule. You can just go back to the lecture if you don't get it. So now if I need to find VL for this circuit, let's just apply the current division rule to find the current. IL would be Is times Rs divided by Rs plus, I'm sorry, this is Ri. So this is the current division rule, and so VL would be IL times RL, and that would be Is times Ri divided by Ri plus RL, and this multiplied by RL. So now I just wrote those two formulas down here. For the voltage source, this is VL, and for the current source, this is VL. So if I want to see how these two sources are linked, I can see that these two formulas are equivalent if I just replace Ri with Rv. For example, if I just assume that the internal resistance of the current source, which is Ri, is equal to the internal resistance of the voltage source. So let's see. If I just put Ri is equal to Rv in this formula, I'll just get VL is equal to Is multiplied by Rv over Ri plus RL times RL. So as we know that ISRV, that's the voltage of the source, because this is the current through the source, and this is the internal resistance. So I can just replace ISRV by the VS, the voltage source. So VL is equal to VS times RL divided by RV plus RL. So now this is very interesting because we got the same formula again. So that means if you want, you can replace a voltage source with a current source or vice versa by just putting the same value of the internal resistance. That means Ri would always be equal to Rv for the same source. So let's just see a practical implementation of this. So for example, if I have this circuit and I want to replace this source with a current source, I could just do this, that I'll just draw the current source here, and because the internal resistance it's in parallel, so the internal resistance for the voltage source is 3 ohms, so the internal resistance for the current source would also be 3 ohms, and then I can just draw the same circuit here, which is the 10 ohm resistor. So, so the internal resistance would be the same. But what would be the value of the current? Now, as we know by Ohm's law, this is an easy way to remember. V is equal to IR. So I is always equal to V divided by R. So just divide this voltage by the internal resistance and you would get the current. So current would be 2 divided by 3. So which is 0.66 ohms. And this is how you can just replace a practical source with another practical source. So I just replaced a practical voltage source with a practical current source. So let's just see another example which will make things more clear. So for example, now I have this source and I want to replace the practical current source with the voltage source. The first thing is I'll just draw the new circuit here. I can clearly see that this is the internal resistance. So the internal resistance would be in series now and the value would be the same, and the entire circuit it would stay the same ahead of the internal resistance. And what would be the value of this voltage source? Well, V is equal to IR, so the current is 3 and the internal resistance is 10, so V would be 3 times 10, which is 30 volts. So this is how you can just replace these two sources. And now in the next video I'll just show a practical example to show why this is very useful in circuit analysis. So let's just see you in the next video now.